Crust-Mantle, Lithosphere-Asthenosphere. It's kind of a strange title, but it emphasizes the fact that these dichotomies are different dichotomies. They're related, but they're different. And intention is to confuse you early, and then the lecture will deconfuse you, if that's a word. So it's time to focus on the plate of plate tectonics. So here we see a nice birthday cake slice of the Earth down to the center of the Earth. And we're seeing all sorts of things, the inner core, the outer core, the mantle, the transition zone, which we'll talk about later, not today. Mantle plumes going up, slabs sinking down, and the plate of plate tectonics is the lithosphere. Those are synonyms. Lithosphere and plate in plate tectonics is a synonym, and we're going to get into this more. And don't hesitate to ask questions. There's only two of you. All right, so we're going to be talking about the difference between compositional layering, which is crust versus mantle, as opposed to thermal or rheological or mechanical layering. That would be lithosphere and asthenosphere. So most students are quite familiar with the difference between crust and mantle. It's a compositional difference, but most students are very unfamiliar with the concept of a rheological, a thermal, a mechanical layering. So we'll spend some time talking about that. And in the lower part of this figure, you see the two major units of the thermal, rheological, mechanical layering, which is the asthenosphere underneath and the lithosphere above. Okay, we're gonna keep digging into this. So how will we discuss this dichotomy? Well, first we'll talk a little bit about the importance of seismology. Then we'll talk about composition versus rheology in a little more detail. We'll get into the compositional differences, crust, mantle, and Moho. And then we'll talk about the continental crust. And then we'll jump over to this rheological layering in the last part. So seismology. So we're going to be talking about this over and over. So there are two kinds of seismic waves. There are body waves and surface waves. So the body waves, these are ones that are transmitted through the solid body. And surface waves are ones that are transmitted along the interface. So the body waves are two types. One of them are compressional. We'll call them P waves, and we'll talk about V sub P as P wave velocity. And then there are shear or transverse waves, S waves. We'll talk about V sub S. And the difference between them is that P waves can be transmitted through solids and liquids, whereas shear waves cannot be transmitted through liquids. So sound is a P wave, if you want to think about it that way. And the body it's being transmitted through is called the atmosphere. Surface waves are two kinds, love waves and Rayleigh waves. And we'll talk a lot less about surface waves than body waves in this course. But in a typical seismograph, you'll see something like, here we have an earthquake, and the body waves will take these kinds of paths, and the surface waves will take these kinds of paths, and we'll see the first arrival is a P wave, and then the next arrival is an S wave, and then we'll see the surface waves. Those are the ones in an earthquake that cause the most damage. All right, so there are two kinds of seismology. There are passive source seismology, where earthquakes provide the energy, or more recently, atomic blasts. So the earthquakes provide the energy, scientists listen. And the seismic velocities determined from passive source seismology, V sub P, V sub S, constrain the large-scale Earth structure. So we sometimes refer to passive seismology as teleseismic studies, basically earthquakes, listening to earthquakes far away. And this contrasts with active source seismology, where the scientists provide the energy, not by blowing up graduate students, as is commonly thought, but by blowing up other things, which used to be dynamite, but more and more are just basically towing instruments that put out, release high pressure air. So these are sort of mechanical farts, if you will, that then they listen to. So this provides more detailed information about smaller features. So, for example, the structure of sedimentary basins, where seismic reflection is very useful, which reaches a few kilometers deep and a few tens of kilometers horizontally. And then crustal structure is mostly not only. Oh, Clint's got a question. Please ask.
Just pointing out, and also on land, they use the seismic vibro-sized trucks that uses the whole truck as a counterweight. And unlike an explosion, which just puts out all the frequencies at once, a truck, or for also these offshore things, they can tune it so that they can put out a frequencies through the spectrum, and therefore makes it easier to do analysis. Back to you, Bob.
Excellent. Yes, so that's especially useful for seismic reflection. In addition, there's larger scale crustal structure, sometimes referred to seismic refraction, which will resolve things a few tens of kilometers deep and hundreds of kilometers horizontal. And this is Dr. Lumley's specialty, seismic reflection using active source. So now let's talk a little bit about the difference between composition and rheology. So composition concerns chemistry and mineralogy. For example, continental crust contains abundant quartz and feldspar. The mantle contains abundant olivine. The core contains a lot of iron and nickel. Okay, that's composition. Rheology concerns how materials behave under stress. For example, under low temperature conditions, rocks will break, and under the same stress at higher temperatures, they will flow, they will bend, they will deform without breaking. So seismic waves are more sensitive to compositional differences than rheological differences.
Dr. Stern, what is olivine? Olivine or what is it?
Olivine is a mineral. It's got the chemical formula Mg2SiO4, and it's
Okay.
the most abundant mineral in the upper mantle.
Okay.
And it's usually pretty green.
Yes, it's usually green. So, yes, good question. I'm glad you're asking these questions. All right,
And the precious version is peridot.
yes. All right, let's talk about crust, mantle, and moho. So crust is the outermost of Earth's three compositionally distinct layers, which are crust, mantle, and core. Crust is separated from the mantle by a well-defined increase in seismic body waves, that is P and S wave velocities. This boundary is called the Mohorovičić discontinuity, and we call it the Moho for short. That is a picture of Andrej Mohorovičić, who was a meteorologist and seismologist from Croatia. And after a severe earthquake in 1901, he and his colleagues established a seismic station in Zagreb. And in 1910, Mohorovičić plotted P wave arrival time versus the distance from the event epicenter for 29 seismometer stations recording a local earthquake. So the idea is the difference in time, the distance versus the time is equal to the velocity. And this defined two trends, one which corresponded to a velocity, a P wave velocity of 6 kilometers per second, the other, which was only seen at greater distances of closer to 8 kilometers per second. Because it's impossible to have P waves traveling in the same medium at different velocities, he reasoned that the two different arrival times represented two different paths for P waves, as shown here. The upper layer has got a velocity of 6 kilometers per second, and the lower one has got a P-wave velocity of 8 kilometers per second. And this defines the Moho, and which separates the crust and mantle. Yes.
So I'm pretty sure I know the answer, but as far as the Moho goes, it's not an actual layer, it's just the contact between the mantle and the crust.
Yes, it's a discontinuity. So this is his sort of original plot. Here's Zagreb. This was the earthquake. This is time in seconds. Oh, I'm sorry, that's minutes. Huh. And distance in kilometers. And these arrivals, you can see that this is a different slope and therefore a different velocity than this. And in fact, we're looking at S waves and P waves. So if we compare the P waves, there's one slope that looks like that, which is the 6 kilometer per second. And then there's this one, which is 8 kilometers per second. And this is how he understood it, right? There, the earthquake focus was in the crust somewhere. And then at certain distances, the first arrivals, right? These are the first arrivals. Whatever happens first is going to be on the lower side of this, are these ones that are traveling at lower velocities. And then at a certain distance, about 720 kilometers, you start to get your first arrivals having traveled through this faster medium. So this made him say, look, there is a boundary between the slower layer, which we now know as the crust, at about 40 or 50 kilometers down, and a faster layer, which we now know as the mantle. And this is the Moho. This velocity step, right? This is a P wave velocity, 6 kilometers steps up to 8 kilometers. So we already said that. This rheological, this is telling you about the composition layers, crust and mantle. Doesn't tell you anything about the rheological layer, lithosphere. But we're going to get into that just so you register. Lithosphere includes the crust and much of the uppermost mantle. Crust and lithosphere are not synonyms. They're not antonyms, but they're not synonyms. Sometimes people will say the crust is the plate of plate tectonics. It is not. We'll get into that more. Lithosphere and plate are synonyms. Okay, any questions on that? All right, so in the laboratory, scientists will study the velocity of different minerals and rocks. And here we see lots of rocks and minerals. And here they are, the abbreviations that we see there. But you can see that the wide range of rocks and minerals, minerals are here in open circles and rocks in solid circles, are on the order of, 5 to 7 kilometers per second, with a mean of about 6.5. And on the other hand, the mantles that make up the mineral, which we know, we'll talk about how we know this, they have higher velocities. So we can confirm that there is this velocity difference from laboratory studies. All right, so let's talk about the chemical composition of the two types of crust versus the mantle. So there are two types of crust on Earth, and we can use P-wave velocities to constrain their compositions because we have these laboratory measurements that I just showed you. So the two types of crust are continental crust and oceanic crust. And these two types of crusts have different seismic velocities, and we'll also see they have different thicknesses and other differences. They're compositionally distinct from each other and from the underlying mantle. So continental crust is extremely variable, but it in average has an andesitic composition, and we'll refer to that by its content of silicon dioxide, SiO2. This is the chemical composition, not the abundance of quartz. students get sometimes confused on that point. But this andesitic crust has a bulk composition that leads to a velocity of about 6 kilometers per second. Oceanic crust, in contrast, has a basaltic bulk composition, lower in silica, 50% silica. I think there's a midterm question that asks you how much silica about is in a basalt. So just remember it's 50%. And it has a bulk composition that leads to a P-wave velocity that's significantly higher than continental crust, right? Closer to 6.8. The mantle, which includes the lower part of the lithosphere and the asthenosphere, has an ultramafic or peridotite composition. So we refer to, sometimes we'll talk about basaltic being the equivalent of mafic. And so ultramafic means it's even more mafic than basalt. So we use these terms ultramafic and peridotitic as synonyms. It's got about 45% silica, and it has this higher P-wave velocity of about 8 kilometers per second. Any questions? Very important. All right, so there's two types of crust, continental and oceanic. And here we can see that's emphasizing something different than velocities, but velocities and densities are related in an interesting way. You see the continental crust has a lower density and it's thicker. Oceanic crust got a higher density and it's thinner. So where we see oceans, we now know that's mostly underlain by oceanic crust. Where we see land, we know that's mostly underlain by continental crust. And then the mantle contrasts with both of these two by having a higher density. Yes, Clint.
And I would point out that when people make diagrams like this, they almost invariably make the mantle look like lava. And this can be, if you guys are aware, yeah, we're talking about rocks, but if you're showing this to somebody that doesn't know about it, it looks like we're floating on a magma ocean.
Yeah, and that's right. There's a common misperception that the mantle is molten, and this is demonstrably false. But we'll talk more about that later. Okay, this is the way I would draw it. So oceanic versus continental crust. Oceanic crust is thinner, denser. Continental crust is thicker, less dense. And the mantle underneath each, there are some subtle differences, but for the most part, the mantle underneath the continents and the oceans are similar. Okay? Oceanic crust is mafic. We said basaltic, but mafic is better because basalt is a volcanic rock, whereas gabbro is a plutonic rock. So this is the same chemical composition. This one cooled slowly, this one cooled rapidly. Okay, they both contain about 50% silica. So we say oceanic crust is mafic for that reason. And this is how oceanic crust forms. What we've done here with this interesting diagram, here's the crust in blue, here's the mantle in red. We've taken the crust away from the right side of the diagram. We're showing the mantle upwelling underneath this is a spreading ridge where the plates are coming apart. And we're going to be talking a lot about that. And here is a very narrow region where the magma is stored that later erupts. It's a very small region of magma, even under a mid-ocean ridge. Okay. So it's basically this pulling apart of the plate here at a mid-ocean ridge that allows the underlying mantle to well up and partially melt. And we'll talk about that also. Now here is a map, a very simple map of the spreading ridges around the world. You've all seen this before. What this one does is it distinguishes between slow spreading ridges and fast spreading ridges and intermediate spreading ridges. It also makes the point that even though we call them mid-ocean ridges, in fact, the East Pacific rise is not in the middle of the Pacific at all. It's way over on the east side. And it also makes the point that in the Atlantic, you have slow, very slow spreading, right? That's a slow spreading ridge. And then it comes around the corner around Africa. And when one branch goes off to the northeast, another branch goes off to the, I'm sorry, northwest. Another branch goes off to the southeast, and it becomes faster spreading as it goes past Australia, between Antarctica and Australia, and then comes around the corner, joins up with the East Pacific rise, where you have the fastest spreading on the Earth happening. Okay. All right, so now let's talk briefly about the upper mantle. It is composed of peridotite. That is olivine. This is a thin section. You can see 1 millimeter. There's lots of olivine in here, and there's a little bit of pyroxenes. Two kinds of pyroxene, clinopyroxene and orthopyroxene. It doesn't matter. These are differences that specialists are interested in. And then there's spinel, which is a different mineral. Now, this is from Texas. This mantle xenolith in this basalt is from Uvalde, which is down by San Antonio. You see a nickel for scale. I had a student working on her PhD on these mantle xenoliths from Uvalde. All right, now basalt is generated when the temperature in the upper mantle exceeds the melting temperature of mantle peridotite. This is a confusing diagram, but still worth discussing. This is temperature, right? 0 degrees centigrade to 3,000 degrees centigrade, which you reach very deep in the earth. This is depth. Surface, 200 kilometers, 400 kilometers, 600 kilometers. There are two sets of lines on here. One of them are the thin solid lines. These show you when the temperature at which peridotite, mantle rocks, begin to melt. And you can see that it's got some interesting topography in there. There are different kinds of mantle rocks because the pressure generates new minerals. We don't need to get into that detail so much. And this is the temperature structure of the Earth. So what you can see is two different geotherms, one which corresponds to oceanic lithosphere underneath the mid-ocean ridge spreading center, gets very hot very fast at very shallow depths, and beneath the continent, like underneath Dallas. So some of you may have wondered, why don't we have any volcanoes in Dallas? It's because our geotherm looks like this, which never gets anywhere close to the melting temperature of these mantle rocks. But out in the middle of the Pacific, where you have the East Pacific rise, it does. So if you just get a little bit above the melting temperature, you'll generate a partial melt, and that can rise to the surface and erupt as a basalt. Okay. If
Is
anybody
that
go ahead.
Is that due to the addition of water changing the melting point?
No. It's what you can see is as you get shallower, the melting temperature gets lower and lower, right? So what all you've got to do is find some way to bring up hot material shallow. And what happens underneath the mid-ocean ridge is because of seafloor spreading, deeper material is brought up, and that causes it to intersect the melting curve. Okay, does that make sense? All right, so let's talk about depth and pressure. So obviously pressure increases with depth in the earth. And the relationship is pressure equals rho GH, where pressure is in pascals, rho is density in kilograms per cubic meter, G is the acceleration of gravity at the depth considered in meters per second squared, And H is the depth in meters, right? So here we will use units of pressure of gigapascals or GPa, capital G, capital P, little a, not the GPA students love, and kilobars, KBAR. So gigapascals is the official, but sometimes we'll use kilobars. But basically, it's very simple. 10 kilobars equals 1 GPa. So just so you know, 1 GPa is reached at something like 33 kilometers deep in the earth, whereas a kilobar is 3.3 kilometers deep in the earth. So do know these relations for midterms, because some questions may be asked that where if you don't understand that, you'll struggle, lose points, and you don't want that to happen. You want all the points you can get. All right. So we talked about active source seismic techniques, reflection versus refraction, right? Reflection, the seismic energy goes in, bounces off something, comes back up. It reflects off of it. So the seismic waves bounce off the interface between the two rocks with different velocities. For example, crust versus mantle. And refraction is the seismic waves travel along the interface and then come up to the surface. So from active source seismic reflection and refraction studies, we can see the, yes, Clint.
So refraction has to do specifically with moving along an interface. Is that correct?
That's correct.
I should know. I've only been studying this for years and years and years. Okay, just checking, because it comes along and it bends anytime it goes through an interface. So that is,
Yeah,
what do you call it? Bending. Is that refraction also?
No, it's a kind of refraction. Any kind of bending is refraction, but the technique that Moho used to discover the Moho, that's I guess you could call it kind of a channelized travel of the seismic energy along the interface, which differs from the broader field of refraction.
We've got to grab us a geophysicist and get them to tell us what the exact term is.
By all means.
Oh no, wait a minute. Maybe they would.
All right. So what we're looking at here is the seismic crustal thickness. So this is basically, we're using seismic techniques to measure the thickness of the crust, and this is the spreading rate of the mid-ocean ridge. So this is obviously slow spreading. This is fast spreading. And what you can see from all over the world, the thickness of the oceanic crust is very close to 6 or 7 kilometers, whether you're going at 140 millimeters per year or 30 millimeters per year. But at spreading rates lower than about 20 millimeters per year, you get much thinner crust. And we'll come back to this later. All right. So active source seismic refraction studies indicate that oceanic crust has 3 layers and is 5 to 7 kilometers thick, as we just showed, with the exception of very slow spreading crust. Layer 1 is sediments. These have variable thickness and velocity, very thin out in the middle of the ocean, very thick near the continents. Layer 2 is the upper layer of the true oceanic crust, which are these quickly cooled mafic lavas and shallow intrusives. And layer 3 is gabbro, which is the slow cooling of mafic magma. So sometimes people subdivide layer 2 into layer 2A, which is basalt, usually in the form of pillow basalt, and layer 2B, these are dikes, which are called diabase, sometimes dolerite, but basically dikes. And layer 3 is gabbro, as we said. Most of the oceanic crust is gabbro. Sometimes people call that the main oceanic layer. Now let's talk a little bit about ophiolites as analogs for oceanic crust and mantle. So ophiolites are on land fragments of oceanic crust and mantle. And here you can see some exposures in Iran. So Hartsbergite is a mantle rock, a peridotite. It's a kind of peridotite. And here we see a pelagic limestone, a sedimentary unit deposited right on top of it or in thrust content. Here we see a close-up of some of these ultramafic rocks, altered peridotite called serpentinite, another kind of altered peridotite called lisfonite. You don't need to worry about those names. Here we see a gabbroic dike in the sequence, and here we see lots of pillow basalts. So ophiolites are taken as on-land analogs for oceanic crustal structure. You know, you might think, well, why don't we just drill straight through it? But that's easier said than done, and we'll talk more about that in a later lecture. So here we see the seismic refraction, the way the active source size marine geophysicists see the oceanic crustal structure, with the ocean on top of layer 1, which can be variable thickness, layer 2, which are basalts and dikes, layer 3, which are gabbros and upper mantle. And here we're looking at what's reconstructed on ophiolites on land. This one is in Oman on the Arabian Peninsula. This one is in Newfoundland in Canada. And this one is in Cyprus in the Eastern Mediterranean. And so you can see there's variable thicknesses that have been reconstructed of the pillow basalts, the dikes, and the gabbros. And you know, there's lots of details you don't need to know about if you're interested. Ophiolites are one of my favorite topics, but I'm not going to bore you anymore with it right now, I don't think. Okay, yeah, maybe a little bit more. So here is an idealized ophiolite section, which was established at a scientific meeting called the Penrose Conference back in the late 70s. So sediments on top, pillared basalts, sheeted dikes, two kinds of gabbro, and then these peridotites. So this is the oceanic crust, and this is the mantle. You know, all of these units need to be present for it to be an ophiolite. Yes, Clint.
In other words, it's basically ocean lasagna.
Well, I'm not sure I understand that one.
Well, it's layered and it comes out as it's made and it's a sheet. So,
okay.
I mean, the whole oceanic crust.
Yeah. Oh, okay. I see what you're saying. Although, yeah, in detail, lasagna is considerably more tasty than ophiolites. But I take your point.
Would columnar basalt be more of a dike as well?
No, columnar basalt is basalt, not an intrusive rock. So that structure happens when the lava cools. Now you can have columnar joining in dikes, but columnar jointing is not a characteristic of whether it was erupted or intruded. But good question. All right, so here we're looking at the Moho in the Samael ophiolite, which is in Oman. So here you have gabbro, and here you have peridotite, kind of reddish, and here a finger is pointing to the Moho. So this gets back to Brad's question, is the Moho a layer? No, it's just a discontinuity. That's not a layer. But that the different velocities of gabbro versus mantle peridotite result in it being a layer that seismic waves either reflect off of or they travel along in a way that would please Mohorovicic if he saw this photograph. All right, so Project Moho, which was started in the late 50s and early 60s, led to a discipline called scientific ocean drilling. So Project Moho was an attempt to drill through the oceanic crust into the Earth's mantle. The American Miscellaneous Society led the effort, one of my favorite names for an organization, which began in 1958. It was include 3 phases. The first was to develop an experimental drilling program. The second consisting of an intermediate vessel program to do drilling, and the third was to consist of the final drilling to the Moho. Phase one began with drillings off of Guadalupe Island, off of western Mexico in 1961. We sampled seismic layer 2 for the first time, and we found it to be basalt. But the project was abandoned when Congress objected to the increasing costs, discontinued the project in 1966 before phase 2 could be implemented. So it failed, but it led to the evolution of the scientific drilling program, first called the Deep Sea Drilling Program, then the Ocean Drilling Program, then the Integrated Ocean Drilling Program, then the International Drilling Ocean Program. And in fact, this one was terminated just last year, so I should change that. So scientific ocean drilling, this is the kind of ship that you use. These kinds of ships are also used in the oil industry, but for very different purposes. And then the Japanese have one. The Chinese are building a couple. There's differences between riserless and riser drilling. So what we can see is, let's talk about riserless drilling. So this is a riser. So the riser is basically another tube that the drill string goes through that basically allows the ship and the drillers to control the drilling environment all the way from the ship down in the drill hole. With riserless drilling, you'd have no control over what's happening. You know, if you hit oil, it's going to spew. Here, you want to hit oil, maybe, and you will contain it. So this is easier to do because the weight that you have to suspend from, including a riser, is much greater than just the drill string. So you basically drill into the ground, and you can core. That's what they do, is they continuously core. Generally speaking, industrial drilling, they don't core. They just drill. Maybe they'll take some cuttings, but really they're not interested in, they know what they're going through for the most part. So this is what was done by this group, this group, this group, and this group all did riserless drilling. And then now the Japanese, this new ship of the Japanese, this is doing riser drilling, much more difficult. And so here's an example of a core that came up on the ship and people looking at the core. And here's a very interesting example of a core. So it's basically, we're looking at 100 centimeters. No, 10, yeah, let's see. Yeah, 10 centimeters. So this is right at the Cretaceous Tertiary boundary. So this is white chalk deposited before the impact. These are sediments deposited right at the time of the impact. And then this is the recovery of the ocean, the environment after the impact. So that's an example of what you might get out of studying a core like this. Now, one of the things that people realize very early is it's very hard to drill all the way to the Moho. So we've tried, this whole 504B is the deepest we've been able to penetrate into the oceanic crust, only on a little bit more than 1.5 kilometers into the crust. You have to get down to 6 or 7 kilometers. So to study the rest of the oceanic crust, people have gone to a thing called offset drilling, where you find exposures of gabbro on the seafloor and you drill into them. That's like what was done at hole 735B. And then there's other places where they've gotten a very small amount of it, and even some places where the mantle is exposed and you can drill into it. But the dream of drilling all the way through an intact section of oceanic crust to the mantle continues today. All right, let's switch over to oceanic crust age, depth, and structure. So this is a really very interesting map. This is the age of the oceanic crust in millions of years. So here we're using red to signify most recent and blue to signify most ancient. And you can see this, the oceanic crust is completely mapped in terms of age, with very few exceptions. And you can see, not surprisingly, that the area around the spreading ridges are where the youngest crust is. They're around the mid-Atlantic ridge, they're in the Indian Ocean, and they're in the East Pacific Rise. And you'll notice that this region of very young crust is much wider in the Eastern Pacific than it is in the Atlantic. And of course, that's because the spreading rate is much higher in the Pacific than it is in the Atlantic. So the width of the area of young crust will be much wider in the Pacific than it is in the Eastern, than it is in the Atlantic. And here you see the very regions of old crust. Here, big region in the Western Pacific. Here in the Gulf of Mexico, along the east coast of the United States, along the northwest coast of Africa, along the east coast of Africa, and along Western Australia. That's age. Down here, we see bathymetry, which is depth. So we can see the continents are blanked out because obviously they're not below sea level. And these reds are shallow regions, and these blues are deep regions. And you see the oceanic trenches, we'll talk a lot about them. These are very deep regions. So the oceanic crustal structure, we talked quite a bit about this. This is simply comparing velocity curves for crust of different ages, 0 to 3 million years, 4 to 5 million years, more than 50 million years old or not. Does anybody see a significant difference in the crustal structure as a function of age? Raise your hand if you do. I'll wait for 5 seconds. 1001, 1002, 1003, 1004, 1005. Nobody raised their hands. That's telling me that none of you saw any significant difference between these two seismic velocities versus depth curves, and that is correct. There doesn't seem to be any difference in the crustal structure of oceanic crust, whether it's young or old. It seems to be sort of very similar. Now let's talk about continental crust. So typical continental crust structure consists of upper crust, which is richer in silica. We call it felsic. Felsic means rich in feldspar and silica, felsic. And a lower crust that's similar in some ways in composition to that of the oceanic crust. It's mafic or gabbroic, right? So the Moho there is shown at 40 kilometers. And sometimes people say there's a mid-crustal discontinuity in the continental crust called the Conrad discontinuity. It doesn't necessarily always exist, but sometimes. Common enough that it warranted giving it its own name. We'll just get back to this diagram. Here we're seeing the differences between the continental crust and oceanic crust. And there's 4 important points we want to make. First, that oceanic crust is made directly by partial melting, somewhere between 1 and 20% of upper mantle. And all silicate planets and asteroids make basalt. There's basalt, we know from some asteroids. We know there's basalt volcanoes on Mars. There's basalt on Venus. We have no problem making basalt by partial melting of the mantle of the Earth or another planet. On the other hand, continental crust cannot be generated by mantle melting. And that is because one of the important constituents of continental crust, granite, is quartz, which is in a reaction relationship with olivine. They can't coexist. So there has to be at least a two-stage process to generate continental crust. Simplified, that would be the mantle melts to generate basalt, and then the basalt remelts or fractionates to granitic magma. So that's a very simple way to make continental crust. The melting temperature of peridotite to generate basalt is on the order of 1200 degrees centigrade, and the melting temperature of hydrous basalt or amphibolite to generate granitic liquids happens at much lower temperatures, only 800 degrees centigrade. When I say lower, you might want to raise your eyebrow at that. When you cook your Thanksgiving turkey, your oven is at no more than 200 degrees centigrade, unless you want to burn it. So it's not exactly frosty at 800 degrees centigrade. So here's a table summarizing it. The differences between oceanic and continental crust, the thickness. Oceanic crust is almost 10 times thinner than continent. The composition, we've talked about basaltic composition of oceans and more andesitic composition of the continents. Now, the age we haven't talked about, but the oldest oceanic crust we know of in the oceans, not in Ophiolites, but in the oceans, is about 170 million years, whereas the oldest continental rock we know is much, much older. It's on the order of 4,000 million years, 4 billion years. We know that oceanic crust is generated by seafloor spreading at mid-ocean ridges, whereas continents, as this is an area of continued discussion and interest, but it's not formed by seafloor spreading. It's formed by some kind of arc magmatism and accretion and all sorts of things. Another big difference is elevation. So we will see that the elevation, the depth of the seafloor is a function of age. The older the oceanic crust, the deeper the ocean. That's true. No, there's no such relationship between age and elevation for the continents. In fact, we will see later in this course that elevation is a function of tectonics, right? We know the Himalayas are the highest mountain, but there's no evidence that they're either the youngest mountain or the oldest mountain. Their elevation has nothing to do with the age of the rocks. We think that oceanic crust is ultimately going to be subducted, removed, destroyed. That's why it's so young overall. And in contrast, the continental crust seems to be basically immortal. Once it's formed, it doesn't seem to go away. And then, of course, the most important difference is the ocean does not have a lot of humans living on it, whereas the continents do. Yeah, there's a few people living in Hawaii and Iceland, but for the most part, people are in Asia, North America, Europe, what we would call continents. All right, so as we said, continental crust is 5 to 10 times thicker than oceanic crust. This is a map of crustal thickness. And you can see that all of these contours are basically around the continents, because the oceans are basically the same thickness everywhere. Okay, maybe there's a little bit thicker crust here and a little bit thicker crust here. But by and large, the interesting variations in crustal thickness are all in the continents. We're going to talk a lot about this one. This is the Himalayas, where the thickest crust on the planet is found. And this one is in the central Andes, the second thickest. And I think there's a midterm question along those lines. So there's an online database called Crust 1.0 you might be interested in. When Walter Mooney talks, you'll learn more about that. This one is it's showing you elevation, right? Here you see the high elevation of the Himalayas and Tibet. And here's the second highest elevation in the Andes. And then there's some high areas of Antarctica because there's so much ice, and in Greenland. There's a few mountains in the western U.S., Mexico, here in Iran, lots of places where there are mountains. All right, so what about, my favorite project was let's drill a hole through the rock parking lot down to the Moho and show those guys that wasted all that money out in the oceans that we could do it much better here at UTD. And if we did that, we'd see there's a little bit of Cretaceous sediments on top, right? Everything, with the exception of just getting west of Fort Worth around Weatherford, you start to get some Paleozoic sediments. But underneath the Cretaceous sediments, including at UT Dallas, there's Paleozoic sediments. And below that, we get into the true continental crust with, 1.4 billion year old volcanic rocks, probably underlain by some granite of the same age, and then a mafic lower crust. And then about 45 or kilometers down, we hit the Moho, and then we're in the upper mantle. Now, this is a satellite map of the Earth's topography. And you can see, again, these high elevations in Tibet and the Himalayas and in the central Andes. Amazing what they can do from space now. Now let's watch a video.
In Jules Verne's 1864 novel, Journey to the Center of the Earth, the characters descend into the crater of a volcano and discover that beneath the surface is a vast cavern with rivers, lightning storms, and even prehistoric animals. This makes for a good story, but what actually lies below the crust is the mantle, a solid layer of the Earth made of a rock called peridotite. Scientists know this even though we've never actually been able to drill a hole to the mantle. This can be surprising considering we first tried to do this back in 1961.
A scientific project is underway, a project called Project Moho, which hopes one day to drill a hole through the crust of the Earth and to find out what's down there.
This project was eventually abandoned in 1966 due to the rising costs, but we haven't stopped trying. So why is it that mankind has not yet broken through the relatively thin crust of our planet to sample the mantle beneath? Well, to start, we need to consider where we should drill. There are two possibilities, oceanic crust and continental crust. Oceanic crust is thinner than continental crust. It could be anywhere from 3 to 5 miles thick, whereas continental crust is from 15 to 40 miles thick. We have drilled deeply into the continental crust before. In the 1970s, the Soviet Union drilled the Kola superdeep borehole to a depth of over 7.5 miles. The project stopped due to the extreme heat that was reached at the bottom of that hole. In general, we see an increase in temperature of around 75 degrees Fahrenheit for every mile deep in the crust. So the deeper we drill, the hotter it gets. We can see that the Kola borehole is about 3 miles deeper than the average thickness of the oceanic crust. So if it had been drilled there, it would have made it well into the mantle. This thin crust is why the ocean is the best place to try and reach the mantle. So let's see what happened to the deepest hole ever drilled in the oceanic crust. To do oceanic drilling requires a drill ship. In 1979, the Deep Sea Drilling Project, using the research vessel the Glomar Challenger, started hole 504B. Over 13 years and 7 visits to the site, each lasting around 2 months, they were able to drill a hole nearly 7,000 feet into the oceanic crust. On the last visit, the hole was deepened a few hundred feet before a fault prevented it from being drilled any further. Drilling to the mantle is clearly more difficult than we first imagined it to be in 1961.
But the planners of Project Moho, intent on finding out what's down there under the sea, believe that the obstacles can and will be overcome.
Drilling through miles of solid rock on a drill ship floating over 2 miles of water is hard, but not impossible. We have the technology and ability to drill to the mantle, and maybe if we tried harder, we could do it. In 2015, the International Ocean Discovery Program started a new attempt at the mantle. It chose a unique spot in the Indian Ocean called the Atlantis Bank, where the oceanic crust is especially thin. They've already drilled over 2,600 feet, and there are plans to return to the hole in 2020 to finally break through the crust. So things are looking up, for the scientists looking down.
All right, now let's talk about, we saw the very simple age relationships of oceanic crust, which is basically, if you know how far you are from the spreading ridge and the spreading rate, you know what the age of it is. That's not true for the continents. You've got this crazy quilt of ages that really you could never imagine. You just have to go out and figure it out. And there are these different units called shields and platforms and origins and basins and large igneous provinces and lots of things like that. I probably need to zip through this because I want to get to lithosphere and asthenosphere. So these are the different units. There's the USGS identifies 6 crustal provinces and their subcategories: shield, platform, large igneous province, basin, extended crust, and origin. And basically, a crustal province is any large tract of continental crust, not including the overlying sedimentary rocks, considered as a whole, all parts of which are characterized by similar features or by a history differing significantly from that of adjacent areas.
Hi, I'm Allie Sealander, and I want to tell you about the oldest rock in the United States. This seems like a straightforward enough question, right? Well, the answer is not as easy as you might think. So where do we look for the oldest rock in America? We can rule out Hawaii, which is composed of volcanic rocks that are only a few million years old. Some rocks in Alaska are much older, dated at more than 2 billion years old. That's pretty old, but still not nearly as old as many rocks found in the other 48 states. To start, we need to look at a simplified geologic map. In this case, a basement map, which shows the age of the crystalline rocks of the continental crust. There are some areas in the US where these crystalline rocks, or basement rocks, are already exposed. But what this map does is strip off the younger rocks that have been deposited on top of this basement. This is the kind of map we want to use to locate the oldest rocks. On this map of the 48 conterminous states, the areas of oldest rocks are shown in dark pink. These areas have basement rocks older than 2.5 billion years, a time period called the Archean. Archean rocks can be found in the upper Midwest and Rocky Mountains. This is where we should start our search for the oldest rock in the US. But wait, how do we even know how old a rock really is? The most reliable method takes advantage of the fact that some minerals contain small amounts of the radioactive element uranium, which decays to lead. Uranium is composed of 2 isotopes, uranium-238 and uranium-235. Both isotopes are radioactive and decay to different isotopes of lead at different known rates. The older the rock or mineral, the more of its uranium will have decayed to form lead. Thus, the ratio of uranium to lead in the rock behaves like a clock, 2 tiny clocks in fact, one for each isotope of uranium. It takes 4.47 billion years for half of the uranium-238 atoms to decay to lead-206, but only 710 million years for half of the uranium-235 atoms to decay to lead-207. One tiny mineral that is widely used to date crystalline rocks is called zircon. The ratio of uranium to lead in zircon can be used to determine the age of the rock. When a zircon crystallizes inside of a cooling body of granitic magma, it contains essentially no lead, so the ratio of lead to uranium is 0. As the mineral gets older and uranium decays to lead, each of these ratios increases, with lead-206 over uranium-238 growing more slowly than lead-207 over uranium-235. Take a close look at this diagram. You can see that the older the rock, the farther up the curve the sample plots. In the ideal case, when a geologist collects a rock, separates out the zircon, and measures the ratios of lead-206 over uranium-238 and lead-207 over uranium-235, and plots these on this diagram, it will plot on this curve and the exact age can be determined. When each isotopic clock gives the same age, the ages are concordant, so the curve is called concordia, and the plot itself is called a concordia diagram. If the two isotopic ratios of lead to uranium don't give the same age, they won't plot on the curve. This tells us that something may have happened that let some lead escape from the zircon. The older the rock, and the more events it experienced over its lifetime, the more likely this lead escape may be to happen. We'll see some examples later. Now, let's get back to our search for the oldest rock in America. Let's take a look at this map again. There are candidates for the oldest rocks in the USA in 3 states: Wyoming, Minnesota, and Michigan. Let's first study candidates from Wyoming, which are found in some of the state's mountain ranges. On this map, the red areas show where the basement rocks are at the surface. Basement rocks older than 2.5 billion years lie within the thick black boundary that outlines the Wyoming Craton. This is what the oldest rocks in Wyoming look like. They formed from magma that crystallized underground, and these igneous rocks were later deformed to varying degrees. The rock on the left is more deformed than the rock on the right. Now, let's look at zircon analyses plotted on a Concordia diagram. These plots show a blowup of a portion of the Concordia diagram for the Wyoming candidates, so it is easier to read off of the age where the analyses plot. Most analyses of zircon from these rocks plot on or near the Concordia curve. Some that lie below the curve indicate that some lead was lost. One analysis lying above the curve suggests that a little uranium was lost or lead was gained. We interpret the results for the plot on the left to indicate that the zircon in this rock crystallized 3.452 billion years ago. That's pretty old, but not as old as the Earth, which is 4.5 billion years old, and not quite as old as the oldest known rocks on Earth, which are in northern Canada and are about 4 billion years old. The plot on the right shows 2 clusters of data, one at around 3.4 billion years ago and another at 3.8 billion years ago. Notice that the age is given with a plus or minus, which describes the uncertainty of the age. The scientists who dated these rocks interpreted their results to indicate that magma that had intruded into the crust approximately 3.4 billion years ago melted an older 3.8 billion year old rock containing zircon. These 3.8 billion year old crystals did not melt or recrystallize, but hung on to their uranium and lead, and therefore remember the age at which they originally crystallized some 3.8 billion years ago. So what is the oldest rock in the Wyoming Craton? Is it the rock we can pick up at the surface that's dated to be around 3.5 billion years old? Or is it the 3.8 billion year old rock that was incorporated into a younger magma, but only its zircon survived to tell the story? Now, let's take a look at the Minnesota candidate. The oldest rocks there are exposed along the banks of the Minnesota River. These outcrops are limited to road cuts, quarries, and riverbank exposures. The zircons from the Minnesota River Valley rocks have been through a lot. The Concordia plot shows this complicated history. Many zircon analyses fall below the Concordia curve. Their ages can be recovered if it is assumed that lead loss happened in one episode. In that case, straight lines through the analyses intersect the Concordia at the time the zircons grew. This sample contains 3 or more age groups, at around 3.52, 3.36, and 2.59 billion years ago, which tells us the age of the rock. The scientists who gathered this data suggested that rocks of 2 different ages, 3.52 and 3.36 billion years, were mixed together during a deformation event around 2.59 billion years ago, which also caused young rims to grow on the older zircons. Let's continue east to the Upper Peninsula of Michigan and look at the rocks there. Old rocks in this area are exposed in an area called the Watersmeet Dome. Here are what the old gneissic rocks in the Watersmeet Dome look like. Some are strongly deformed, as on the left, and some are less so, as on the right. As you see from the data plotted on the Concordia diagrams, almost all of the analyzed zircon have lost lead, and the data form an array along straight lines. Zircons on the left plot define a line that intersects Concordia around 3.68 billion years, and on the right, around 3.6 billion years. Both also have clusters of analyses that plot on Concordia at around 3.62 billion years. There are also a few zircons that are even older. These are interpreted as inherited from even older rocks, one as old as 3.8 billion years. Does that date sound familiar? It should. It is the same age as the older group of zircon grains from one of the rocks from Wyoming. So, how old is the oldest rock in America? Is it the Michigan gneiss that has been dated to be around 3.6 billion years old? Or is it the Wyoming rock that contains 3.8 billion year old zircon crystals? Well, it's complicated. But one thing does remain clear. The oldest rock in America is at least 3.5 billion years old. It is interesting that the three occurrences in Wyoming, Minnesota, and Michigan line up, suggesting that a belt of very old crust trends across the northern United States. Maybe with more investigation, more candidates will be discovered for the oldest rock in America. Thanks for listening.
Okay, now we know the ages of the crust for different regions. This is age versus the number of zircons we have. So we can see is the age of the crust, is created, continental crust is created it pulses. So a big pulse at 2.7 billion years, another big pulse at 1870 million years, and here we are today. We don't have any crust to speak of from older than about 4 billion years. I think we're going to move very quickly. We will, the midterm does talk about craton, shield, and platform. All three of these terms refer to the stable interiors of continents. Craton is ancient crust that's been stable for a long time. It's composed of igneous and metamorphic rocks like all crust, continental crust. Shield is exposed craton, like the Canadian shield. Platform, like where Dallas is, down here is a craton that's covered by younger sedimentary rocks. So craton is the larger group, shield is exposed craton, platform is buried craton. Orogenies, orogenic belts, and orogens, these are places that have been created by episodes of crustal deformation that generates new crusts and mountains. By definition, cratons are not affected by orogenies. Orogenic belts are elongated belts of high relief and deformation, like, say, something like the Andes or the Himalayas. And orogens are crustal tracts that were deformed at about the same time. So they're all related to this mountain building. So this is sort of the crustal provinces of one way of looking at the crustal provinces of North America. Now we can break that out into ages. In fact, the ages of the crust in North America are quite different. The oldest rocks are up here in the north in this gray, and then these get younger and younger. And then we get the Grenville belt added on the side. And all of this, the Cordillera, has been added since about 1 billion years ago. So we've drilled into continents in a couple of places. We mentioned the Kola Peninsula, which is the deepest drilling anywhere. We got down to 11 kilometers. And there was another deep drilling hole in southern Germany, in Bavaria. We got down more than 9 kilometers. We've done nothing like that in North America. I wish we would. We don't need to talk about this. Okay, to summarize the lecture this far, the Moho separates the mantle from the crust. There's two fundamentally different types of crust, continental and oceanic. The lithosphere in our modern definition includes the crust and the uppermost mantle. And again, crust and lithosphere are not synonyms. Lithosphere and plates are. But now let's talk about the lithosphere. So lithosphere is the plates. So Earth's tectonic plates, here we've got all the plates, that constitutes the lithosphere. So these are the plates. These are the big 7. Right? The Pacific is the biggest. This is the area in millions of square kilometers, 108, right? And then Africa is number 2, Eurasia, Indo-Australia, etc. And then these are sort of the medium-sized plates, Nazca, Arabia, Caribbean, Cocos, Philippine, and a lot of smaller ones here. And then some of them are growing and some of them are shrinking. The Pacific, the biggest plate, is shrinking it's losing about 52 kilometers per 100 years because it's being subducted. So now let's talk about lithosphere versus asthenosphere. Lithosphere is the rigid outer layer of the Earth required by plate tectonic theory. The crust is the upper part of the lithosphere, which is mainly composed of mantle. Lithospheric mantle differs from the underlying asthenospheric mantle in terms of its rheological, its flow properties, not its chemical composition. So under the influence of low intensity, long-term stresses that drive plate motions, the lithosphere responds as a rigid shell while the asthenosphere behaves as a highly viscous fluid. The weaker mechanical properties of the asthenosphere are due to the fact that this part of the upper mantle is hotter, maybe also because of some fluids. Asthenosphere, and this is the important point, the asthenosphere lies beneath the lithosphere and provides the weak substrate for the lithosphere to move on. It allows plate tectonics to happen. So this is seismological evidence for lithosphere and asthenosphere. Now, this is a little confusing. This is S-wave velocity. This is in French. So in P waves, we were seeing the crust and the mantle being a boundary of between 6 and 8 kilometers per second. P waves are slower than S waves. So this step here is showing you the Moho, very shallow. This is oceanic. So that's corresponds to the seismic velocity of oceanic crust around 3.5 kilometers per second. And then it steps up to about 4.5 in the upper mantle. Now we're going pretty deep here. And what you see here with the S waves is there's this, usually it's just increasing with higher and higher pressure all the way down, except in this one area called the zone of, this is the low velocity zone, LVZ. That's where the shear waves actually get slower with depth. And remember, shear waves are sensitive to the presence of fluids or melts. They're not transmitted in liquids. So this has been taken as evidence that this is a zone where it's close enough to melting that there's a little bit of melt in there and maybe some fluids. This low velocity zone, documented by shear wave velocities, is thought to be the asthenosphere. Okay. Any questions on that? That's the point that students often get confused, not just because of the French. We are fairly confident about the top of the asthenosphere, but if you assert certainty about the base of the asthenosphere, I think most seismologists and scientists that know anything about it would raise an eyebrow. So there will be no questions about the depth to the base of the asthenosphere on the midterm. All right, so this is another one. This is for near the spreading East Pacific rise, and this is shear wave velocity, right? V sub S, right? So here we're looking at the crustal velocities would be somewhere there. That's the oceanic crustal thickness. So all of this is in the upper mantle. And what you can see is right below the crust, the shear wave velocity is like 4.5 kilometers per second. And then as you go down to about 40 kilometers depth, it is on the order of 4. It's a significant decrease in velocity. That's the low velocity zone there. That's the asthenosphere in this part of the world. So we look at it something like this. Here we've got the lithosphere, which includes the crust and upper mantle. The crust is that gray stuff. This looks like a mantle plume. That's a spreading ridge. This is a subduction zone. So we've talked over and over again about the upper part of the mantle is the only part that melts, and there we see that beneath the mid-ocean ridge. And this asthenosphere is basically everything below the lithosphere. And you notice that the lithosphere is very thin beneath mid-ocean ridges and very thick with distance, right? And here's the lithosphere under the continental crust, which is much thicker. We'll talk about all of these things. So plates can contain different proportions of continental versus oceanic crust. So plates can include only continental crust, for example, Asia, only oceanic crust, for example, the Pacific, or some kind of a mixture. The North American plate contains most of North America continental crust, but it extends all the way to the mid-Atlantic ridge, so it's sort of a mixture. And the nature of the crust on a plate strongly influences its behavior. We'll talk more about that. So here we're looking at continental crust. There's oceanic crust. This is mantle lithosphere. You see this deep keel underneath the continents that extends deeper than the oceanic plates. And later we'll talk about the fact that the plates that move the fastest are the ones that don't have continents on them, because this kind of a keel sort of slows down the plate. And then underneath that is the asthenosphere. So we can look at a map of continental lithosphere. Remember, we looked at a map of continental crust. I'm not sure. Do we get another one? Yes. So we looked at a map of continental crustal thickness. We saw these regions of thick crust. But look, the maps of lithospheric thickness are quite different. The thickest lithosphere is up here in Europe or in Western Australia or in Western Africa. It's not up here in Tibet or in the central Andes. There's really no relationship between the crustal thickness and lithospheric thickness, which is confusing to students, or should be, but it is one way to make an additional point about the difference between compositional layers and rheological layers. This is a rheological layering. This is a compositional layer. Okay, so to look at this diagram from the perspective of this map, the lithosphere thins to very thin beneath the mid-ocean ridges. You see it here. Everywhere there's a mid-ocean ridge, you have very thin lithosphere, just like we see in this cartoon. Underneath the continents is where we have the thick lithosphere. All of these regions of thick lithosphere are underneath certain parts of the continent. This one is where the Canadian Shield is. This one is another craton, the European craton. This is another craton, another craton, another craton. Cratons have, because they're long stable, they have thick lithosphere. So there's a number of definitions of lithosphere we don't have time to get into. All right, so there's different definitions of lithosphere, and this, there's a number of reasons why students get confused about lithosphere. One is, the ideas of crust and mantle are very well embedded in our brains, whereas lithosphere and asthenosphere and the whole concept of rheology is much less intuitive. And then we add this, the definition of the lithosphere, but it's useful to talk about it. The top of the mantle is relatively cold and strong boundary layer, which we call lithosphere. Because it's strong, it can't convect, and so heat escapes to the lithosphere largely by conduction, and also occasionally by upward transport of migrating melts and volcanoes. The thermal structure of the lithosphere is controlled by conduction. Another way to define lithosphere is that lithosphere is Earth's thermal boundary layer. So the concept of a boundary layer gets back to, we were talking about blankets, insulation. And in contrast, beneath the lithosphere and the asthenosphere, the heat is transported by convection. So lithospheric temperature gradients are characterized by conduction. So, so there's a very large change in temperature with pressure or depth, whereas the asthenosphere temperature gradient is characterized by convection. It's got a very small change in temperature with depth. Right? So there are three ways that we can move heat. One is by conduction, which is what the lithosphere does. Another is by convection, which is sort of the movement of heat because of density. And the third is by radiation. So this is Fourier's law of conduction. Heat flow is proportional to the temperature gradient. So the heat flow Q is equal to this constant K, the conductivity, times the temperature gradient, right? So if we can neglect radiogenic heat production, which for the most part we can, then the temperature gradient is linear in a conductive solid. So for say 100 kilometer thick lithosphere with it's 0 degrees at the surface and 1300 degrees at the base, which is what we think the asthenospheric temperature is, that dTdz is, by simple math, 13 degrees per kilometer. So the continental crust, in contrast to the oceanic crust, contains a significant amount of radioactive elements, especially potassium, uranium, and thorium, which produce heat. So conductive geotherms in the continents are a little steeper. Normally, it's about 25 degrees per kilometer in the continents, as opposed to the oceanic conductive geotherm. Convection, the temperature profile is controlled by convection. And this term adiabatic is basically that heat is neither lost nor gained as a result of convection. So for that temperature gradient, dT/dz, that's equal to this equation, which is the coefficient of thermal expansion times the gravitational constant times the temperature divided by the heat capacity. And in contrast to the continental, to the conductive geotherm, which is on the order of 10 to 20 or 30 degrees per kilometer, the convective geotherm, the adiabatic geotherm, is on the order of 0.5 degree per kilometer. It's very different. that temperature structure between the lithosphere and the asthenosphere is this very, very different. So we get a temperature profile like this. You know, this part where the temperature doesn't change much, that's the convective geotherm, the adiabatic, you know, less than a degree centigrade per kilometer. And up near the surface, you know, it's greater than 10 degrees per kilometer. And we can argue that the oceanic geotherm, you know, gets hotter faster because it's just younger, and the continental one is more like that. So now, one of the papers in the readings, if for those that want to learn more, is this paper which of Anderson, 3 definitions of lithosphere. One of them is thermal lithosphere, which he quotes as the outer shell of the Earth where there's a conductive temperature gradient overlying the well-mixed adiabatic interior. And this definition of a lithosphere equates it with a thermal boundary layer, TBL. You don't have to know that for the midterm. It's useful to have heard about a thermal boundary layer. When I first heard about it, I was confused. But it's basically, you know, if you understand intuitively about thermal boundary layers, because most people put on more blankets at night in the wintertime than they do in the summertime. They're just making their thermal boundary layer thicker and more insulating by doing that. So the base of the lithosphere is generally thought to correspond to the 1200, 1300 degree isotherm, which approximates the melting temperature for mid-ocean ridge basalts. Now, as Anderson also talks about another definition of a lithosphere, which is mechanical, the elastic or mechanical lithosphere, the ability to support loads. So this thickness is determined by seeing how the plate bends when it's loaded, such as outboard from trenches, where the plate is actually bent to go down into a subduction zone, around oceanic volcanoes like Hawaii, where you put a load on it by just piling lavas on top, and in other places where you've removed a load, such as glaciers in Scandinavia, where the lithosphere is flexing, recovering, and the seafloor is the land is rising. So the base of the mechanical lithosphere, in contrast to the thermal lithosphere, is about 600 degrees isotherm. So it's about half the thickness of the thermal lithosphere. So that's another reason you should be confused by the definition of lithosphere. We got these 2 different definitions. And then there's another definition, which we won't spend much time thinking about, and that's the chemical difference. But we will talk about thermal lithosphere and mechanical lithosphere in this course. The mechanical lithosphere is related to the elastic thickness of the lithosphere. The silicates flow more easily at higher temperatures. So the lithosphere appears to be thicker at low stress levels and over short time intervals than at high stress levels and long time periods. That we can skip through this. And then finally, he talks about a chemical lithosphere, where the lithosphere is that part of the Earth that doesn't mix, right? It's basically because it's not flowing it convectively like the deeper mantle does. It doesn't mix. So we don't need to get into that, but it comes from isotopic arguments. Now we can talk about viscosities. Viscosities are usually reserved for describing liquids, but it has been useful in describing the difference between lithosphere and asthenosphere. So viscosity in Pascal seconds. For lithosphere, the viscosity is much greater than 10 to the 24th. For asthenosphere, it's significantly lower, 10 to the 21 or 10 to the 22. Now that is, those are huge numbers. Sort of steel has got a viscosity of about 10 to the 13th. So these are astronomical viscosities, but these differences between lithosphere and asthenosphere viscosities are useful for modelers.